Hi guys, welcome to part two of this review that basically I know we did a lot of it in class and there were some questions, although we did some of them actually the ones that are questions that you guys had, we did them also in class, but you wanted some sort of a summary of things. So I'm going to go through the questions that you have. Anyway, I am looking in here at problem 9. Basically, it tells you a block of mass m starts with a negligible speed from the top of an incline of angle theta. Coefficient of friction is mu k, as shown below, using Newton's laws to find the speed at the bottom and show that it is in agreement with the law of conservation of energy. So we need to find the acceleration. Then, since the height h is given, then the angle theta is given, so I can find the distance it traveled. Then, based on that, I can find the velocity. So let me share with you the other resource quickly here. So I have an incline. It doesn't matter. It has to be. It doesn't have. So this height is h. The angle is theta. The coefficient of kinetic friction is mu k, and after I tap it, it moves. And this is mg. This is the normal n, and this is the force of friction, and it's kinetic friction because it's moving. So F equals to ma means that the force of friction plus the normal plus mg must be equal to ma. And in this situation, I have, because it's moving, Fk in magnitude is equal to mu kn. And I project this expression both in the x-axis and the y-axis. X-axis along the incline. So along the incline, I have minus Fk. The normal has no component, and mg has a positive component. Since this is also the angle theta, by a geometrical argument, we can argue that this is theta. So I'm looking at the opposite to theta, which is the sine of theta. Mg sine theta must be equal to ma. And then furthermore, in the y-axis, or at least the perpendicular direction, we have the Fk has zero component, the normal is positive. I'm taking this direction to be positive. And then minus mg, and now I'm dealing with the adjacent to theta, which is cosine theta, must be equal to 0 since this is not moving up and down. From here, we can solve for n, and n turn out to be equal to, okay, mg cosine theta, and this gives me the force of friction then equals to mu k mg cosine theta, and plug it into this expression. Finally, I can find the acceleration. The acceleration being ma divided by m. That expression gives me the acceleration. A equals to g sine theta minus, because the m cancels all the way throughout. I have, even in Fk, I have a mass in here. So it's going to be minus mu k g cosine theta, I think. Okay. So g comes out as a common factor in here, sine theta minus mu k cosine theta, and that's the expression overall, okay? For the acceleration. From here, we can find we use the expression that gives it the velocity, basically, squared minus the initial velocity squared, which is equal to 0, by the way. We did this expression when we did the beginning mechanics, times 2a times the displacement that it moves. This mass moves from this point in here when it's tapped all the way to down, and this distance d from the hypotenuse in this case is related to the opposite through the relationship of trig functions. D is equal to h over sine theta, okay? Because h over the hypotenuse d is equal to sine theta. So from here, we can find the expression for the velocity, namely the velocity squared is equal to 2 times g times this stuff in here, which is sine theta, times 1 minus mu k over 10 theta. I mean, I took sine theta just as a common factor. That gives me the acceleration, times 2, of course, times the distance, and the distance happened to be h over sine theta, and cancel the sine theta over the sine theta, and the expression actually is going to be expressed in terms of the ratio of mu k and sine theta. Okay, and then the square root, of course, you get the v. Using the energy directly, we can do the energy directly to find this expression. And here also, the change in the kinetic energy is equal to, or the change in the total energy is equal to the work of the non-conservative forces. So delta E is equal to WNFC, work of non-conservative forces, NCF, I'm sorry, non-conservative forces. And the only non-conservative forces in this case is Fk, the force of friction. And the work for it is going to be a negative number because Fk is pointing this way and the displacement is in this direction. So the dot product of these two will end up being negative. So WNCF is going to be a negative number, mu k times n times the displacement d. Okay, and the displacement d is exactly h over. We just argued for it. N is just mg cosine theta. Again, you have to solve the kinematics to find this expression over sine theta. So that's basically the work of non-conservative forces. When the mass was tapped, initially it did not have any potential, did not have any kinetic energy, but it had potential energy. So the total E naught in the beginning is 1/2 times mass times 0 squared, that's the velocity squared, plus mg times h, that's the expression for potential energy. And when it reaches the ground, in that case, it's 1/2 of mv squared plus 0 potential energy. So the change, so this is E1, E1 minus E2 is delta E. So 1/2 of mv squared is minus mgh is equal to minus mu k mg cosine theta, or mgh over tan theta. It's the same thing. That's the expression. Cancel the m from both sides in here and move the 2 to the other side and move the gh to the other side and take the gh as a common factor because there is a g and there is an h in there. So v squared will turn out to be exactly 2g times h times 1, because you will be left with 1 minus mu k over tan theta. Exactly like similar to the previous expression. Of course, you have to take the square root to find. Oh, I forgot the h in here. There is an h from this expression here. I forgot to carry over. Okay? Yeah. It's this h. Okay? So it has to be. I mean, dimensionally, it's not correct to have only 2g. 2g is just acceleration. Anyway, so that's basically a problem. This problem, let me go back to see what we have again. Okay, it's in here. We did this one in class today in detail. This one says in here, a trolley of mass m is released by compressed spring. So you compress the spring, you give it potential energy, then you release it. That potential energy is converted to kinetic energy. And the kinetic energy must be enough so that it stays on the loop in here and comes out. And basically, that's the whole problem. And how far it's going to slide in the region when there is mu k. So let's go back into here and see if we can analyze the problem. So when it's on the loop, you need an energy, you need a velocity in such a way that the centripetal acceleration in here, this is mg, and this is a normal. Again, it's coming through the loop, inside the loop. It's not outside, it's inside the loop. So the normal in this case, plus mg, is equal to ma. And a is equal to v squared over r, that's in magnitude, and n is positive and mg is positive. Both of them are radii pointing toward the center, is equal to mv squared over r. In order for it to remain in contact, n must be greater than or equal to 0. So n, which is equal to m times v squared over r minus g, must be greater than or equal to 0. Otherwise, if it's 0, then in this case it came off of the thing. So the minimum velocity then in this case that makes this one true is v squared equals to rg in order to make the loop. This is the minimum, not, okay, this is the bare minimum, okay, velocity. Well, in this case, the kinetic energy then for this trolley is going to be 1/2 of its mass times velocity squared, or 1/2 times mass times this value, rg. So this is the minimum kinetic energy that it needs, and this kinetic energy was a potential energy in the spring, and the spring potential energy 1/2 of kx naught squared. So this must be equal to 1/2 of mRg. And from here, we can find the value for x naught equal, cancel the 1/2 from both sides, is equal to the square root of mRg divided by k. Okay, so this is the minimum compression of the spring that you need in order for it to make it on the loop. Then furthermore, it goes to on the loop and then comes out, and that energy is going to, at the end, is going to vanish in such a way at the end the total energy is going to be zero, because there is no potential energy, there is no kinetic energy. However, the initial kinetic energy is going to be 1/2 of mv squared. Remember, there is no potential. We are on the same level at this point. Okay, when it reaches the surface, this surface where you have a mu k, it comes in at this point and ends at this point. So mg h is the same. There is no gain or loss in potential. So in this case, potential energy is zero. We're going to take the height to be zero in this case. So the only thing that is actually the total energy, the kinetic energy. So the change in the kinetic energy is equal, the change in the total energy is equal to the work of the non-conservative forces. So the final value is this, the initial value is that, so it's minus 1/2 of mv squared must be equal to minus mu k times, in this point in here, the normal is equal to mg, whereas the force of friction in this case is equal to just mu k times n, and n is equal to mg times the distance it moves. So I'm going to call this distance d. This is basically an express condition for me to finding the distance it travels, d, and the distance is going to be, cancel the mass again of the trolley from both sides, cancel the negative sign also on both sides, and I will be left with 1/2 v squared over jd. Okay, remember v squared is actually rg. V squared is rg, so it's going to be 1/2 of rg over dg. Cancel the g from both sides. Oh man, what's the d in here? What am I doing in here? Sorry, there is no d in here. That's the d from the solution. Basically, mu, we're solving for d in here, so why did I have a d in the denominator? Sorry about that. Mu k in here. Okay, so at the end we find the d is equal to just 1 r over 2 mu k. The distance d is equal to r over 2 mu k. Okay, that's basically the answer to that question. Let's move along. Again, you're supposed to do the whole review by yourselves, and if you have any questions, please let me know. Again, this we did it in class also. It was an extensive one. So basically, for this problem in here, the y components of the forces cancel by symmetry, and the only component that remains is the x component of these two restoring forces minus kx. So I will have a minus kx in here and another minus kx pointing in this direction. So, but there are two of them in this direction, so it's minus 2kx, but times the cosine of this angle. And the cosine of this angle is x divided by the hypotenuse, which is square root of x squared plus l squared, because this is a right angle triangle. So that's basically what we have in this case. The force is going to have these two components, and the force itself is minus k times this whole thing, the elongation, minus k times the elongation. So let's try to build this quickly in here. Let's see how we're doing in time, with 14 minutes on time, so we're good. So again, we have a spring along this direction. This is x, and this is L. Okay, so the initial length of the string is L. Now the new length is clearly square root of L squared plus x squared. So the elongation of this spring is the new length minus the length itself, the length at rest. So all I have to do is just write this force, which is equal to k times, again, it's a negative because this is I hat, it's in the negative direction. So the force is minus 2 of them, because there is another one I didn't draw in the bottom. 2 times the elongation, and the elongation in this case is going to be equal to L squared plus x squared under the square root minus L times cosine of this angle. Because again, we're just projecting in the x direction only, times the cosine of this angle, and the cosine of this angle is actually the adjacent, which is x divided again by that square root of L squared plus x squared. Obviously, when I throw in this inside, this becomes 1, and I will have minus 2kx, and the x is coming from the cosine, times 1 minus L over square root of L squared plus x squared, as it should be. We're asked to show that the force in this case points in the negative x direction, and it has this magnitude, okay? And it's 2 of them, okay? Let's look at the problem again and see what other questions they're asking. I know they gave us a potential, and they want us to show that the potential is where the force derives from. So they said 2k, the potential is ux kx squared plus 2kl times L minus x squared plus L squared. All you have to do is take the derivative of this potential and show that its negative is actually the force itself. In other words, all I have to do is show that the derivative of u with respect to x with a minus sign is the force in the x direction. The force in the x direction is exactly this expression. Obviously, I don't have force in the y direction, otherwise I would be having partial derivatives, and the other one will be minus the derivative with respect to u with respect to y, and that will be fy. So in other words, in general, fx is actually minus partial derivative of u with respect to x, whereas fy is partial derivative of u with respect to y, and fz is a partial derivative of u with respect to z with a negative sign on each and every one of them. But we don't have any other component other than the x-axis, so we don't have partials. We only have the straight derivative, the standard derivatives. So in this case, all I have to do is take that potential, which is equal to not potential, u is equal to 2kx squared plus, let me look at it quickly in here, 2kl times L minus square root. Plus 2kl times L minus the square root of L squared plus x squared. Okay? For some reason. Okay. And in here, all I have to do is take this derivative and show that indeed it's that potential. Finally, let me check something in here. Make a plot of u. So we're going to plot u. So let me pause this thing quickly in here. How are we doing on time? We still have good. So let's plot this potential in here and show indeed that it has a u as if identify the equilibrium and some r equal to 1 point. So basically, you need to plot this function. Obviously, it has a quadratic form in here, but don't forget you have this square root in here, and that you're going to show the equilibrium and all of that. So let me get GeoGebra going. I know we used it last time, and actually let me get another one in. I don't want to confuse the two in here. And the potential is, let me move the potential to the other screen for a moment so that you can see it. So u of x, first of all, do we have the value of k? Yeah, I'm going to plug in the values of k that they gave us in here so that we can plot it. It's 40 times 1, and L is equal to 1.2 meters. What else do we need in here? That's it. So u as a function of x is equal to kx squared equal, oh man, can't do that, equals to kx squared plus 2 times k times L, open parentheses, L minus the square root of x squared plus L squared plus L squared. That's a potential we have in here. Okay. Make a plot of T. Assume that if the particle is pulled 0.5 to the thread, then released. So we plotted it. So indeed, there is an equilibrium in here. Okay. You can clearly see it near the origin. And if you're not sure, just take the derivative and equate it to 0, and you're going to find the derivative equal to 0 at that point. So we can find the insolve of derivative of u equals to 0. Practically, it's 0. When you see this number in here, 10 to the negative 7, it's practically 0. I mean, this is a numerical solution, so don't. So when you see n solved, that means you're finding a numerical solution, so it's going through a lot of steps and you're trying to find it. Anyway, so this is going to be the equilibrium, and then we can find the potential there. It's clearly 0, because when you plug in x equals to 0, this term is 0, and this term is L minus L, which is 0. So that's the minimum potential in there. If the particle is pulled half a meter away to the right and then released, I'm reading the problem. What is this? It's the speed when it reaches x equal to 0. So again, we need to find the energy at that point. Okay, when it's released from less, we take it half a meter away and we let go of it. So we need to find the potential energy at that point, and the potential energy is 0.4 joules. So when it reaches the minimum, when it reaches going through that, that means at that point there is no potential energy. All of that energy is kinetic. So the kinetic energy is going to be equal to this value minus 0, because at that point the potential energy is 0. So the velocity v is going to be equal to the square root of twice the mass, twice the kinetic energy, and the kinetic energy is just that 0.4 divided by the mass, and the mass is given to be, how much is the mass in here? Did they give the mass? I'm trying to read the problem in here. Yeah, 1.18 kilogram. M is given to be 1.818 kilogram. So we really needed the mass. M equals to 1.18 kilogram. So this number actually is not correct. We have to divide it by the mass. Okay? No, incorrect. We have to go back, and let me delete this and put 1 in there. Probably there is an easier way of doing it. So divide by, here where we divide the mass, inside the square root. So it's 0.82 meter per second. That's the maximum speed that it's going to go, because that's what it's going to go through the origin. Okay, I hope that this has been helpful. And if you guys have any more questions, I'll be more than happy to discuss them with you guys. Thank you.